I'm recording. Let me see some things. Yeah. So hi. This is kind of be a Accelerator Physics lecture intro that I decided to come up with because on YouTube there's nothing that exists that does Accelerator Physics lectures. And first of all, if you're a physics major, if you start undergraduate, you will not learn about accelerator physics typically. And if you, even though you go to your PhD, you will also not learn about your accelerator physics classes. You'll basically learn about classical mechanics, quantum mechanics, E&M and stuff, but the accelerator physics left out. But indeed, if you go to accelerator physics sector, then there's specialized courses that usually advisors send you to twice a year to learn about these stuff. But then when you actually get there, it's actually 1 or 2 weeks maximum classes where they just squish all all semesters worth, or even a year's worth of classes into just 2 weeks, and then you just don't really learn much. So the scope of this is accelerator physics. I'm using Remarkable to record this and write stuff. Well, it feels nice to write on, but it's just like when you turn to new pages and stuff, flip around pages, kind of laggy, but it does the job right. It is what it is. So to start with, if you want to learn accelerator physics by yourself as well, you have to go S.Y. Lee's book, S.Y. Lee, Accelerator Physics, and Wiedemann's particle accelerator physics. And these two books are really resourceful, and of course you can find online resources, a bunch of presentations and stuff, but none of them actually show you in detail calculations, but they give you nonetheless a pretty good overview, and PowerPoint style lectures and stuff that they skip a lot on details and stuff. And this first video is just gonna be a kind of test introduction video, so I'm not gonna go so much details until if I see what I have to fix and stuff, because I've never done this before. That's what she said. Never done this before. And then and then see what happens. As preliminary, we need, in other words, the things. I broke my marker, so it's funky. The things we need to know are classical mechanics, like Newton's laws. From Newton's law to at least if you go up to Hamiltonian / Lagrangian dynamics is very useful. Then we have classical electrodynamics, E&M, such as Maxwell's equations and motion of charged particle under electric and magnetic fields and so on, like cavities and stuff like that. We have statistical mechanics, which is because we're dealing with more than one particle, so ensemble theories and stuff like that. Not necessarily entropy and stuff, but in terms of accelerator physics, one way to think about it is also plasma physics, so that goes into statistical mechanics part. A little bit of quantum mechanics, and also special relativity is a must. So these are kind of preliminary knowledge that we should know before getting into this subject, and I guess this will become clear as we move on. So I guess to start with, the main question is what is accelerator physics? And it's an interesting question because in the early ages, accelerated physics was thought to be part of what do you call part of particle physics, because at those times people were coming up with theories of new particles and stuff, and how can you get to them via collisions, and if you want to collide them, you have to be within range of applicable energy, and how to get those energies, then you have to accelerate particles. So initially ACCX for accelerator physics was subfield of particle physics, and it became clear because people were coming with QED theories, quantum electrodynamics, and QCD came, then EW, electroweak theory, and standard model, and so on and so on. And then the search was, like smashing protons and antiprotons, electrons with anti-electrons. Now, even right now, people talk about smashing muons with mu plus anti-muons. So these ideas were only successful if you reach, well, depending on your energy scale of interaction, but if you reach at high energies or medium range energies, but you have to go from whatever you started from and some initial energy to E high or desired. So since this is like a basically idea to go from one energy to another energy, accelerated physics was thought to be a part of particle physics. But then it turns out that this is not actually true, and accelerated physics kind of gained its own freedom later. For example, medical physics. And the reason medical physics was that the first thing to come to your mind is cancer slash radiation therapy. And this is basically, if you start with some isotope, bunch of protons, neutrons, and then the whole atom or isotope can be thought as a particle, and this will be shot through your body, go through, and as it passes through, it will start ionizing some stuff. And if the cancer's cell is here, then it will try to hit this, and then by ionizing the cancerous cell, basically destroy it. But then the moment that you see this, then you will have to ask this question. So what is this distance, which is usually called skin depth, skin depth, and usually skin depth, which is given by skin depth, the length it takes to ionize the isotope or whatever you have, alpha particle, electron, or whatever you might have. But it turns out that this skin depth delta depends on kinetic energy, so you should be able to calculate the kinetic energy that you desire. And initially you start with some initial energy, E0, initial, whatever. So to go from this energy to this energy, you have to accelerate your particles, or isotopes in this case. Therefore, this also belongs to accelerated physics discipline. So all this research on medical physics, and especially in cancer and radiation therapy, belongs to accelerated physics field. Another thing that we can talk about is, for instance, an institution that exists, APS, or Advanced Photon Source, and the name stands by it, photon source. And this is where some QM, quantum mechanics, come in play with electrons. And the electrons Why? Because they have such a small mass. Mass of electron is really small. I'm not gonna say put one, but like it's really small compared to other particles. Therefore, as a particle goes around a circle, let's say an electron moving this way, then it switches direction to move this way, and is achieved by a dipole magnet. Let's say this is a dipole magnet which has some magnetic field, and it just bends the particle as it passes through. And then if you know you're from classical mechanics, anything that goes around a circular path with a radius r experiences a centripetal force, which accelerates, right? And if you know a charged particle that accelerates, it loses energy through emitting a photon. Now this photon usually is in the range of X-rays, and this photon can come, once you produce it with the correct energy spectrum that you wish to have, you can send it through some kind of a lattice or whatever structure that you just came up with in your basement, and shoot it through with photons, and this photon will scatter off inside here and come up with an, let's say, angle, and you can have a detector around this and detect basically this angle scattered, which is Bragg scattering, I believe. So you can deduce this angle, you can calculate this angle, and this angle will tell you the infrastructure of your unknown material or crystal, usually crystal-like structures that you came up with. So you can also use diagnostics purposes that relates to accelerator physics, and I believe the list goes on. For example, lasers is also part of accelerator physics now. There's like, you know, quantum computing is also getting into this part. So the list, yes, goes on. Now that we've established that, I want to. I mean, the initial question to ask is what type of accelerators exist, right? So okay, so we just established, you know, we can accelerate them, sure. We can use them for particle physics, for discovering new particles or not discovering new particles, depending on your choice. Or yes, some cancer research, which is very useful, or finding out the new materials, that properties and so on, or like other applications that. But like, how do we achieve this, right? So what type of accelerators? As I mentioned, this is the kind of introductory test video, so I will see if I'm doing something wrong or something right after this. Well, there's a couple types. First one I can say is Van Graaff generator. So this guy is designed as like a little globe one, and another globe here, and this globes I believe have some metal inside, and there's like this static band that, you know, moves up and down, and with the act of moving up and down, it carries basically particles like an elevator up here. This thing is charged. Let's say if it's charged, minus here, plus here, and the electrons here, as it passes, it gains energy, and it comes here, gains another energy, and then it's electrostatic acceleration, which doesn't give you so much energy, but this was back then a lot of energy considered. So OG accelerator physics. Next thing was Betatron. Betatron came up. Don't remember the design, but we'll talk about it. And then Microtron came up, Cyclotron came up, and Cyclotron is very interesting, easy. You have these two Ds, these nuts, where you connect these ends to an alternating current, source, which AC source means that the polarity, so if this is plus and minus in 1 second, the second is minus and plus. So it rotates plus and minus. Now, why do you need to do this, right? So if you place a charged particle here, and also another extra information that these D's are some metal, or maybe probably iron, they have magnetic field crossing them, which means you have some magnetic field, let's say, is coming outwards or inwards, depending on your charge of particle. And you can use, physics too, right-hand rule, FPI, to figure out the force of the magnetic field will act on this. But the idea is this: if you place a charged particle here, it will see a constant field pushing it. Let's say this is plus charged. Then this guy here will accelerate towards this plate. And with the remarkable, I can change the color, red. So as it accelerates here, this way, it's immediately faced with magnetic field. And this magnetic field, because it's perpendicular to the direction, so if you come this way, the magnetic field, we can place it like this, inside. Then, I guess doing FBI, FB is inside, I, then the force will be, when you do your right-hand rule, you will realize that it's going to be this way. So the particle will go through and rotate around. As it rotates, you want to flip this polarity, so you're going to have plus and minus, as we mentioned, because the current changes direction. So if you get plus, then now you accelerated through this gap again. Now you started with some energy, accelerate a little bit, and then you accelerate again. As you accelerate again, you're going to do a bigger curvature, bigger semicircle, then paste it again with the plus and minus sign, get pushed through, then do a bigger one, and then repeat this cycle. And then once you hit the end, usually you know where you should hit, so you can make a hole here, and this hole you can extract your particle. So this is how like cyclotron works. And if you ask what's the kind of relationship you have with the circles, we can go back to black. Once you go black, and if you remember from physics 1, you have circular Newton's second law, of course, is ma. But if you have circular motion, which we see that this is what's happening with the magnetic field, we have mv squared over r. Now that's cool, because this is how circular centripetal acceleration is written as, AC. Now you have to figure out what the FC is. What's the force actually causing this? Now we talked about there's a magnetic field perpendicular to that location. So if we have magnetic field or an or electric field, then we are dealing with Lorentz force, which is given by dp dt, which is force, charge, E field plus charge, E velocity vector times crossed with magnetic field. Here is charge, E field, velocity, magnetic field. So if you only have magnetic field, because imagine this, you just entered the D's, so inside the D, no E field. So E field is 0. So we have the force only being EV cross B. And from the cross product, you know that if this is perpendicular, which is in our case, through the direction of propagation, then you can write the force as EVB. Because V cross B can be written as magnitude of V, magnitude of B, sine theta VB, So the angle between these directions, but then since this is pi over 2 or 90 degrees, we have this factor being 1. So that's why we can write it as EVB. So EVB is this force that's causing the centripetal motion. Then we equate this to mv squared over r. So what we get is v's cancel. We have b times r is mv over e, which is br momentum, because m times v is momentum, over e. Now this is a very important result. And as we can see, what does it tell us? If the magnetic field is constant here, if I drag this to here, so br equals momentum over e, if b constant, then we have br p over e. And remember, we are accelerating through this gap, so we're changing our momentum, which means we are moving faster. If b goes up, then due to this equality, r has to go up. So r has to go up. That's why we have a higher radius of curvature here. We have increasing the radius, we're increasing the circle that we are making, and then we just exit. And once we exit, there's no b field, so that's it. But this equation is very important, and typically, if I go on next page, typically br equals p over e is written as b rho p over e. And this is what the equation that you see in Accelerator Physics, where rho is the radius. Therefore, if rho is the radius, this is this is called in general magnetic rigidity. And magnetic rigidity is an important term in accelerator physics because it tells you what? It tells you b rho is p over e. I'm just rewriting everything. Means depending on your energy slash momentum. Energy and momentum is related, as we know from special relativity or just classical mechanics. Then for a given radius, we can calculate the magnetic field. So if when you're designing an accelerator, let's say a circular accelerator, then by knowing this radius that you just pick, you can decide on maximum B field required to bend given energy of particle. Now it's very important in design of magnets, because if for a certain radius you have to have a first maximum magnetic field, then but in real life you cannot achieve the magnetic field, then what is the point? So this gives us this gives us kind of a solid foundation of what on deciding numbers and what's feasible and what's not feasible. It's a very important equation. So this is how the cyclotron works, and then the other one is called synchrotron, which is kind of latest technology, and latest meaning like 1960s, but it is used almost everywhere. For example, CERN, Fermilab, Tevatron, what else? SPS, Oak Ridge, and so and other places in the world. And synchrotron is a circular machine that looks, probably maybe if we draw it this way, it makes more sense, where this is basically a pipe and you have magnets or whatever all around the circle, and you have some places where you have electric field, let's say here, let's say here, let's say here, and every time the beam goes through this pipe, every time it faces one of the field, energy increases, goes around here, energy increases, goes around here, energy increases. So this is basic foundation, I guess, of certain types of accelerators. But the thing is, when you say circle, it's misleading, because later we'll see equationally, I guess next probably video, that the only way in real life to bend beam or collection of particles, or just a charged particle, is through dipole magnet, which looks like basically tubeless on scheme. Here's a particle that there's a magnetic field outwards. Sorry, this is wrong drawing. If I erase this, basically, if you have, let's say, let me use FBI. Okay, so if we have a magnetic field that looks like this everywhere constantly, then we have this motion. So the particle gets bent through only dipoles, magnets, which dipole magnet meaning this, where you have magnetic field constant in upwards direction, let's say here, here it's inwards direction, and the particle gets bent through. But and then there's other magnets that exist that we'll look at. But if this is the case, and you assume you have a circle, that means the whole circle is just a bunch of dipole magnets that look like this, which is not true in real life. In real life, you have dipole magnets finite length, not the whole length of your accelerator. So it means you have, let's say, a dipole here, straight, dipole here. My drawing sucks. Straight, dipole here, let's say, straight. So as you can see, it will be like this. So it's technically an cornered polygon. So it's not really a perfect circle, and the end just depends on number of dipoles. So it might look like this, and the more the number of dipoles, the more closer to a circle that you will look like. So yeah, but on the first approximation, circle is fine for calculating stuff. Okay, guess like a little bit of overview of that. And next thing is, I guess, like one mathematical background that you should know is simple harmonic motion, or SHM for short. And this is just differential equation. If you see a differential equation that's in the form of this, then this is your simple harmonic motion. And I mean, it's straightforward to solve this from your differential equation class or physics, I guess. I don't know, maybe one solves this. And to solve this, you just assume a solution, and it depends on time, some constant cosine omega t plus some constant sine omega t. And if you plug this to here, then you're going to find out that this is the correct solution that you guessed, because it will satisfy that equation here. So, but we're not done here, obviously, because we don't know what A is, we don't know what B is, and that's where initial value problem comes in. And what is the initial value problem? That means to find out these unknown coefficients, we have to say what's the y value at time equals 0. So initially what we're starting with. But instead of writing, writing it like this, we can just assign some value, y0, some constant. And if you plug time equals 0, cosine of 0 is 1, sine 0 is 0, we are left with a. So we immediately find the first constant, first unknown. To find the second one, we have to take the derivative, dy dt, t equals 0. And this will give us negative a omega sine omega t plus omega omega b cosine omega t. And if we plug in time equals 0, and we can label this as y dot 0, first derivative of solution, 0th, then we will get omega b. So we found now b is y0 dot over omega. Therefore, solution is y of t, depending on for all times now, y0 cosine omega t plus y0 dot over omega sine omega t. So this is like how we solve this, and for given some initial values and knowing what omega is, assuming it's a constant here, we can solve this, and even you can plot it as a time domain, which will be sinusoidal wave, and so on. Okay. Now the next important things to know is Maxwell's equations. And Maxwell's equation, when we say Maxwell's equation, we should know this. Divergence of electric field is a charged distribution divided by epsilon 0, which is the permittivity of free space. Divergence of magnetic field, always 0. Curl of E is time derivative of magnetic field. Curl of magnetic field is permeability of free space, current density vector, plus 1 over c square dE dt, time derivative of electric field. So yeah, so Maxwell's equations, and then these tie to Lorentz force, which gives us dp dt is E plus V cross B. Right. On the list that we should know. But then there's also important aspect. Let's get a new color for this baby. I don't know. Let's do red. Well, there's white option, which doesn't make sense. It is from the special relativity. Total energy square is p square, momentum square, c square plus m square c to the fourth. Now, from classical physics perspective, the total energy is kinetic energy. If you don't have anything else, if you have some other phenomena like like hills or springs, we add a potential energy. Excuse me. But if we assume we are not moving, we assume we're at rest, so P is 0, then you can see that the total energy is mc square. So this relates to Einstein's idea. So from special relativity, as I mentioned, this equation gets reformed as this equation, which holds true now that we include the rest mass, or the energy that a body has while just sitting down, which is mc square. Everybody knows this. What's so interesting about this? So if you write total energy as square root momentum square c square plus m square c to the fourth, right? And we say, well, in accelerator physics we say we are accelerating. But what does this mean actually? Like, what do you mean? Yeah, sure, we're accelerating, but equationally, what does it mean? It means that our total energy is increasing, right? Or in terms of total energy, kinetic energy is increasing. Or to be more specifically, we are gaining speed, or we're gaining momentum. So as we see this logic tray here, then this is just common sense, right? If our total energy increasing, we are accelerating, which is we're moving faster, so we're moving. Just these two things mean we are moving faster. Our kinetic energy is increasing, or our momentum is increasing. But if something is increasing, we can do derivative with respect to time. So we can ask question: how fast is this thing increasing? So which transforms equationally, just taking derivative of this total thing. And if we apply the differentiation rules, we get 1 over 2 square root p square c square plus m square c to the fourth, and then c square 2 p vector and dp dt. And let's just apply differential equation, differentiation rules. You know, we have square root, which is this thing raised to the 1/2, and when you take the derivative, we move the 1/2 to the front, where this 1/2 comes from. Then we subtract 1 from the power. This is how we get 1 over square root. And then since this is just whole thing is one operation, we have to differentiate inside as well with respect to time. Now the mass and speed of light doesn't change with respect to time, obviously, but only thing changes is momentum. So this is how we get this factor here. We cancel some 2's, and we realize that this term is exactly what we started from. So we write it as c square, the total energy, p dot product with respect to dp dt. So this is what we left with. But then, okay, so we relate the total energy change with respect to the change in the momentum. Cool. But we know what the change in momentum will be in accelerator physics, because we only have electric fields or magnetic fields. So dE dt, dE total dt, is c square et p dot ee plus ev cross p. Now we just inserted the Lorentz force in there, and if we expand this, what we get? Take e out, e plus c square e total p dot v cross p. And you might ask the question, okay, cool, so what can we do actually with this idea? The thing is, we can also write momentum as mv, as you know, and only substituting this to here on the second part, we get c square e total energy dotted with E electric field plus c square E over total energy mass V velocity dot with velocity cross V. And the importance of writing this term, in this term, we get, if in general we have a vector A dotted with itself crossed by another vector, this is always 0. And it's very obvious, because if we introduce a different vector C and call it A cross B, when you take a cross product, this result always perpendicular to A and B. So you're finding basically the third dimension. For example, if I take X cross Y vectors and you get Z, so it's like, this is like how you find this. This is X, this is Y, this is how you find Z, this way, which is perpendicular to both to x and y. So since this is how it's done, and it always gives perpendicular vector, I'm just gonna erase this quickly, this part. Cool. But if you look at a dot b, this can be written as the magnitude of a, magnitude of b, cosine of the angle between these two AB. So if you have this, then this is the theta. If this is a, this is b, some random vectors, or theta AB. Cool. But then if I take a dot c, I will get a c cosine of the angle, which is pi over 2, which is 90 degrees, which the cosine of 90 degrees is always 0. So this is always 0. Always. If the angle is 90 degrees, it's always 0. Therefore, this product here always vanishes to 0. Always. Just from the perpendicularity of the vectors. Which means, let me just erase this arrow so it doesn't confuse. If we go right, which means, it means that if we look at the rate of change of the total energy with respect to time, we get whatever, c square E over total energy we started with, momentum dotted with electric field. Which means, I can write it in a more barbaric way, the rate of change of total energy is proportional to electric field, which means only electric fields can accelerate charged particles. So we just established this relationship that the only way to increase our energy is through electric field. Therefore, this will suggest that to accelerate, use E field. To manipulate slash guide, use B field. Very important result, and we only got it from just like this, doing the simple analysis on the total energy. Gives us the fact that the only way to accelerate particles is through electric field, and we cannot accelerate particles through magnetic field. But also, like, if you follow Maxwell's equation, you might ask very interesting question. You might say, but with like 8,000 T's and exclamation marks, we know that there's a Maxwell's equation that exists. Del cross E equals magnetic fields derivative. So if you only have magnetic field that changes in time, it produces electric field, which can be used to accelerate particles, which is actually the Betatron's principle. But I was given examples of microtron, cyclotron, so Betatron's principle is based on this idea. But this doesn't violate above statement because E field is created by B field. So in the end we have E field, so that we're just going to create E field to accelerate, which is cool. Yes, this kind of ending of the intro slash test video. For next, we're gonna go in more formally talk about I shouldn't give names before explaining them. More about dynamics. Find BE fields. Look at Lorentz force. Interestingly, yeah, and move to actually solving real stuff. Yeah, I guess that should conclude. Maybe see you next.